time is the first all virtual meeting, and we have a record of 406 people registered, so we are pretty excited about this.
Buenos días a todos mis colegas latinoamericanos de habla española. Buen día a todos meus colegas brasileiros. I hope that everybody is doing well across the Americas in these pandemic times.
Our theme this year is Bridging the Americas. This is an effort to build relationships and collaboration while serving our early career community and others who may be disadvantaged by COVID-19. It's great to see, really a global representation at this meeting.
I think that one of the most interesting things that we have found is the influence of FPAR by wind speed. And one of the things that we have observed this consistently on our sites in Germany, in the UK, in Canada, and in Costa Rica, is that as wind speed increases, there is an increase in the standard deviation, but also a decrease in the mean FPAR being calculated. And that there is a threshold around 5 meters per second where actually everything goes loose. So we have been recommending in some of our publications that wind speed must be part of activities associated to a measurement of FPAR and actually filter data of FPAR over 5 meters per second.
And here the question was, how was the rainfall partitioning in this kind of vegetation? And we found out that rainfall interception is very important. We consider that it's important because it reduces the amount of useful rainfall for the plants or for recharge. In this case, this canopy could hold up to one millimeter. It was the storage capacity of this canopy. And altogether, it could reduce by 20 to 30% the gross rainfall.
So this is just an schematic of the sites, some around 14 sites that we gather information and fluxes. So in this site, the covariance has been going since 2015, and NIDA's work found very interesting things. There is an important difference on how the fluxes occur in this site. Early succession and secondary succession of these are actively growing forests. The net ecosystem production is high. There is a net carbon gain every year in this forest, but surprisingly, the old growth forest seems to be a net source of CO2, where we have instrumented a pair site. This is also historic data, where we instrumented two mangrove ecosystems, one that is in a quite pristine area, not towards the northern part of the country, near Isla Tiburon, which is an awesome place that you need to visit if you want to get to know the Sonoran Desert. And then another one laying right a few kilometers from where I am right now, right by the Yaqui Valley, which is highly impacted by anthropogenic activities. Agricultural drainages hit these estuaries, and those seem to be having an effect on the carbon and water fluxes, which is what we see in these bottom graphs. One of the sites, the more pristine side, the more preserved side, is a stronger both are net CO2 sources, but the more preserved side is a stronger sink of carbon. And of course, there is a bunch of questions open, but we believe that all these agricultural drainages that exacerbate ecosystem, perhaps it's attenuating the potential of carbon sequestration from these mangroves.
We mainly promote interagency cooperation and coordination. We involve the science community in providing the needed science to understand the carbon cycle, to help secure funding and prepare individual and joint agency initiatives. And we're also instrumental in the process of prioritization of U.S. government cycle science research streams. The scientific framing for Soccer 2 was based on the 2011 U.S. Carbon Cycle Science Plan, and I will not go through all of those. but that is the basis for all of that. And this is more on soccer too. We reviewed over 3,764 publications, and we've worked with over 200 experts across 3 countries.
So we brought this model into and wrote it into a carbon offset protocol. And that protocol kind of outlines all the steps in which you would develop a wetland and then constrain the greenhouse gases exchange in that ecosystem and then get carbon credits for that restoration process. And so the American Carbon Registry approved the protocol, and they're the ones that oversee all of the carbon credits for California's cap and trade system. And it was first used this past spring in 2020. So the California Department of Water Resources actually used the protocol for the first time, and they had a wetland restoration project of 1,700 acres. They received about $62 per acre. We're expecting this number to go up in the future as this moves into the compliance market. Right now it's only operating in the voluntary carbon market. And this was a really great example of how you can directly link eddy covariance measurements and with models and use that to help us inform carbon markets. So something that kind of came out of that process was identifying some of the weaknesses. So there was a huge data gap for this system in California, which is tidally influenced wetlands. And these are really interesting systems because they have complex carbon cycling with both the atmospheric exchange of CO2 and methane, carbon burial, and then the lateral exchange of dissolved inorganic and organic forms of carbon. I also wanted to highlight that these ecosystems, are in stark contrast to the freshwater peatlands I mentioned earlier. They have very, very small methane budgets, and which makes them a little bit easier to operate in the carbon market community. The mitigation potential is a little stronger, and the radiative forcing is a little more straightforward and immediate. This also kind of led into the methane working group under the Coastal Carbon Research Coordination Network, which is also a group that's very focused on connecting flux data with stakeholders. And I'm co-leading up this methane group with Ariana Arias-Ortiz at UC Berkeley. And what we're working on right now is bringing together methane flux data from all coastal wetlands in the United States, and using that data to inform and develop models. One we're working on right now is the MEM peppermint model. So we're bridging this marsh equilibrium model with the peppermint model. And then we're bringing all that modeling product into an open source modeling tool GUI format. And so users can type in the coordinates of their wetland and give us some information about the site. And then they can run MEM peppermint in this GUI and get outputs of greenhouse gas budgets, soil accretion, and also, really importantly, uncertainty in their estimates. And just want to emphasize, particularly with carbon markets, the more uncertain your budget is, the less offsets you receive.
An operational system for mapping evapotranspiration at field scales for the Western US at daily, monthly, and annual time steps. The system provides information both summarized for individual fields as well as the wall-to-wall or gridded satellite data products at the original Landsat resolution of 30 meters by 30 meters, or about quarter acre per pixel. As we zoom into individual fields simply by moving the cursor over a field, and then you can also get annual ET summaries and cumulative time series for each year to do this. Again, with just a few clicks of the mouse. The reason I picked this field to highlight in this example is that this is a field in Grand Valley, Colorado, where there was a incentive-driven water conservation program. This grower participated in that. And you can see the difference between 2016 and 2019, where they were up around 34, 36, 38 inches per year, versus 2017, where they were enrolled in the program for the entire year, and ET dropped substantially, and then again in 2018 when they were enrolled for part of the year. So this ability to quickly and easily measure the impacts of investment in water conservation, investments by growers and advancing on water use efficiency is really important, I think, to scaling a variety of solutions for sustainable water management in the West. I think the intercomparison and accuracy assessment we're doing as part of OpenET is the largest intercomparison done to date for remotely sensed ET data. We're using information from flux towers. This is really central to the effort we're undertaking right now. Also bringing in publicly available groundwater pumping records, in part because that can be a compelling comparison for agricultural partners. And then at larger scale, looking at water balances for well-characterized basins from USGS studies across the West.
Many people have been starting in our field, have been starting talks with this figure, for going on 15 years now. And I just want to propose that maybe we've got a new figure that we'll begin to see at the start of some of our talks. And this is the climate mitigation potential of a host of so-called natural climate solutions. So there's a lot to unpack in this figure, but the main thing that I want you to look at today is the size of these error bars, which for some of these strategies is really, really wide. Now, we know that these natural climate solutions are not a panacea, right? So how can the AmeriFlux community help reduce uncertainty about the potential of natural climate solutions, right? Where is this particular strategy a good idea? Where is it a bad idea, right? How can we narrow those error bars on that Hargioni graph? And so the first thing I'm going to suggest is that you go to Kyle and Ben's breakout session on Thursday, which is dedicated to the topic. And the expectation, the theory suggests that by the time a forest gets to be about 100 years old, it will be more or less carbon neutral. Right? So if I can just boil a whole lot of work done by a lot of people into a few numbers, here is the annual NEP or NEE from these 8 years of measurements from these 3 towers, right? And here's the Odom hypothesis, and we can put our data on the Odom hypothesis. We can say, oh, it looks pretty good over here, right? But look at our 80-year-old hardwood forest, still a strong carbon sink. We can also add in AmeriFlux data. That's the beauty of the network, right? Because still just one chronosequence in one place doesn't tell us much. But here I pulled in flux towers from the eastern United States. Here color-coded by plant functional type. And we can see that the Duke Forest Tower was not unique, right? There's a lot of mature deciduous hardwood forests in the eastern US that are still soaking a lot of carbon out. The punchline is forests keep us cool.
My colleague Allison Thompson and I 10 years ago sort of made the first attempt to synthesize, to actually go through the tail and synthesize everything. And that's not everything. You have to make some choices about what you're going to do, or else you'll never finish. And that's a point I want to return to. But to synthesize data into an open community database. There are problems though with this, okay? For all that I think SRDB has been useful, both as a model for the open science in our communities and also in carbon cycle science. It has problems. It was built by a clueless amateur at the time. And so, there are decisions I made 10 years ago that I would love to get back if I could, and it's laborious. In other words, right, so if it's not deposited, say in a permanent repository, if you're just dependent on the mechanism of reaching out to people to get their data, it's about a 17% per year loss of taxpayer-funded, right, data. This database, I pronounce it COSOR. Margaret Torn and I are going to have a discussion with exactly the pronunciation, but it's oriented towards continuous, so these continuous data sets, and tries to build on sort of, at least for me, some lessons learned. So emphasizes data provenance, traceability, has a lot more automated error checking built into it, in QA/QC generally. It's set up for programmatic use from the get-go. So it's a real structured database. It has a much cooler name. And as Elizabeth Wokowicz and colleagues, made the nice point, in an era of global change, our measurements are irreplaceable. They're not reproducible. And so that tick-tock weighs heavily, I think, on all of us. But this balance is something to think about. I think this, the long tail grassroots efforts versus sort of the potential of bigger, some more centralized efforts, and they're both necessary. And in particular, how I think all these efforts, these open science, open data efforts, particularly benefit junior researchers and researchers and scientists with fewer resources. And that's a benefit. It increases access for the entire community, and that's a good thing.
Okay, so I'm reporting back from the soil moisture group. And so in line with that, we spoke a little bit about the idea that plants can actually serve as our soil moisture sensors in many cases. So we talked a little bit about how the community with regards to soil moisture is perhaps a little bit like an ostrich with its head in the sand, but actually maybe the birds don't have it totally wrong.
The analysis, I'm going to talk about mainly based on data from the orbiting carbon observatory 2. OCO2 was launched back in 2014, and it has been collecting about 5 years of data. Then we look at the biome-specific relationships. CIF was strongly correlated with GBP for all biomes, except evergreen broadleaf forest. For the tropical biome, we had a very limited number of data points. This is really encouraging. Given the strong CIF-GBP relationships at the ecosystem scale for a wide variety of biomes, we might be able to directly use a single satellite observation, CIF in this case, to estimate GBP. This way, we could avoid the use of many input data such as climate, soil properties, and so on, that we normally use for the estimation of GBP. This way, we could avoid many sources of uncertainty at the regional and global scale. So with the established CIF-GBP relationships and OCO2 CIF soundings, can we map GBP globally? We are not quite there yet. The OCO2 data are still spatially sparse. Of course, we could aggregate the individual soundings to cause resolution grid cells, but even if we use like a 2-week window, there could still be a lot of data gaps across the globe.
So left figure shows that the semi-arid ecosystem contributes the most to the interannual variability of atmosphere CO2. And with climate change, drylands are also expanding, so it will have more power to impact the global carbon uptake. From a remote sensing perspective, there are key limitations when you use vegetation greenness index, such as NDVI, to estimate the dryland production. So the left figure also showing the high heterogeneity of dryland ecosystems with a relevant percentage of tree cover, grass cover, and soil background. The study area will focus on 22 flux tower sites with GBP processed across semi-arid western US. So we further classified these 22 flux tower sites into tree-dominant, grass-dominant, shrub-close, and shrub-sparse. Satellite NRV and CIF actually improved the predictions of GBP across the dryland sites. Especially the Tropomi CIF shows improved predictions for the GBP dynamics across the dryland evergreen forest sites, but it also with their limitations at the low productivity sites. And then reflectance-based indices show significant hysteresis loops with GPP. The reason could be the relevant percentage of the trees at those sites.
We started with a model a few years ago where PIs would send their methane data directly to us, to Sarah, and then also Gavin McNichol at Stanford, and they would work with the PIs to get that data processed. We've now moved towards a model where the methane data are first hosted on regional networks, and then the PIs work with FluxNet methane. And then I also need to acknowledge that FluxNet methane exists thanks to the data providers. So we have many people who have contributed to setting up the towers, to going out into the field, to collecting the data, maintaining the towers. And this is PIs, this is postdocs, this is technicians, this is graduate students, this is undergrads. This is so many man hours have gone into collecting this data and to the willingness to contribute it to FluxNet methane. So this data set exists thanks to them. So let's just take a little bit of a deeper dive into what this data set looks like. So we have, as I said, 81 sites. So this is encompasses, we have 2 lake sites. We have 7 rice sites. We have 22 sites that are, we call upland, and we break this down more in the metadata, but this includes things like alpine meadows, it includes agricultural lands, it includes forests and different types of forests. have 5 salt marsh sites. And then our largest category is freshwater wetlands, and we break this down into bog, fen, marsh, mangrove, swamp. So we have these 5 different types, 44 of them all around the world. Now, if you look at the annual flux range for the methane, we see that there's a heavy tail on this. So the over 200 site years of data, the average methane flux across the entire database is about 17 grams of carbon per meter squared per year. The median that is about 10. So we have a lot of sites with relatively modest methane fluxes, but then we have a fair number of sites that are a lot higher, and even one that's over 100 grams of carbon per meter squared per year. But basically, the lighter the color, the more representative flux net methane is of that type of wetland, and then the darker the color, the less well represented that wetland is. So, for example, you can see up in northern Canada, there's a large extent of wetlands, and by and large, those wetlands are reasonably well represented within flux net methane. Same with Northern Europe, Russia. But then when you go down, you look at South America in particular, and then Africa, there are large expanses of wetlands in these areas that are less well represented in the flux net methane. And this is not surprising to us. The circles show tower locations in flux net methane, and so we have very few in these tropical ecosystems. And we hope that this sort of dissimilarity analysis can show the way forward for areas and ecosystems that we really need flux towers and measurements from to try to improve our understanding of methane dynamics from these wetlands on a global scale. So if you plot the points from all of our site years of data at all of our freshwater wetlands, this is what you get. You can see that almost exclusively methane does not start to increase at a site until the soil temperature has already begun to warm up. And the lag there on average is about a month.
Collaborations are really important moving forward. Make sure that you actively engage our growing network of sites and partnership sites. And this includes, partnerships that we've been developing over the years with the NEOM community, with ICOS, with Brazil Flux and Asia Flux, and all the different flux communities. Collaboration is the key there. And participate in those communities. Serve on the committees, lead census. Again, it's the same thing. It's that this is how we move this community forward for the next 20 years. One thing that I ask that you do as part of the AmeriFlux community is continue to make diversity, equity, inclusion, and a safe work environment part of our culture. Don't forget to include psychological safety and harassment prevention as part of your operational plans. There's a website there that'll take you to DOE's research conduct policies, including things with diversity, equity, and inclusion, and scientific integrity. So I encourage everyone to think about not just the Band-Aid and boo-boos type of things that we do in the field, but inclusion and psychological safety as part of our operating culture moving forward.